Okay, in this particular lecture we will be doing uh, another clustering algorithm which is called OptX. OptX is the short form. The full title of the algorithm is ordering points to identify clustering structure. Uh, Now, as the name indicates, this algorithm, although apparently it does or it performs clustering, but if you read the last three words in the name of the algorithm, so the focus of this algorithm is to identify the structure of the clustering instead of identifying the detailed clusters, right? So this helps in uh, identifying the number of clusters that the data may have, and then you can use the output of this particular algorithm as an input to another algorithm. For example, if this algorithm suggests that there are 4 clusters in the data, then what you can do is that you can use this 4 by setting a value of k equals to 4 for the k-means or k-medioids clustering algorithm. So but again you can use this algorithm to perform clustering itself as well, depending, it totally depends on how you program your solution. And now the DBSCAN, like if you recall the DBSCAN algorithm, you were supposed to provide the input parameter epsilon to that particular algorithm as an input, which is fine, that only one or couple of algorithms were needed by the DBSCAN algorithm. But for a real world problem, which is usually the data is high dimensional, and especially in the present era of big data, the data is has got a lot of dimensions plus a lot of instances as well. So setting the epsilon straightforward is quite hectic, and maybe you need to give multiple values, and you will need to have multiple uh, settings of epsilon, and then you may find a good solution for that. So in such situations, OptX helps you uh, to avoid this issue. The method of clustering, this method of clustering orders the clustering the objects in a specific manner. Let's come to direct to the algorithm, where the data which is required for this particular algorithm is actually the two major features. One is that you will need to provide this algorithm the minimum points, because as you recall, DBSCAN as well, minimum points are required for algorithm to classify a point in the data as a core point, right? So that this minimum points is also required for OptX as well. And then here another parameter which is labeled as epsilon, but it is called generating distance. It is also required for this algorithm. This is the largest distance considered for clustering, right? So you will be providing these two parameters to the algorithm. Now for every day, or for every variable in the data, or rather for every instance in the data, for example, this instance, this instance, this is another instance, this is another instance, this is another instance, and this is another instance. So for every instance in the data, we will have to record or keep track of two points or two variables or two values for each and every data in the for each and every point in the data. And what are these values? One is the core distance, and the other one is the reachability distance. For every point, we will store these two values, and but we need to know that what are actually these two values. So the core distance of any point, let's say core distance of this point, is the smallest distance or is the smallest radius epsilon dash that makes the P as a core object, right? But this E dash will always be less than this E which we provided it to provided to the algorithm initially. So for one for example our E is, let's say, 10, right? So maybe maybe for this point our E dash may be, let's say, 3, for this point our E dash may be 8, and for this point our E dash may be 9, right? So for each object we need to store the core distance for that object, and then we need to store the reachability distance for that object as well. And what is the reachability distance? Now the reachability distance of Q from a core point P, right, is it is the core distance of P, right? If this point is within the radius of P, then the reachability distance of Q is the core distance of P. Otherwise, if it is not within the radius, which is the E dash radius, then it will be the Euclidean distance between these two points, right? So to explain this point further, let us consider a visual representation here. Now if we see here, consider that we set the minimum number of points for our optics algorithm as 4. Now if we see here and let's see our E which we give to the algorithm is 6, but at the distance of 3 we get the minimum number of points around this point P. So this P becomes a core point, and its core distance will be 3, right? Now consider the graph or example on the right side. Here if you see it is the same example, but we have labeled 2 more points, that is Q1 and Q2. Now the reachability distance of Q1 from P will be 3 because it is within the core distance of P. Although if you see here this distance is less, but since it is within the core distance, that is the epsilon dash, so instead of setting the specific distance which may be 2, we are setting its reachability distance to be 3. But if you take the case of Q2 which is outside the minimum radius epsilon dash, so there the reachability distance between P and Q is not epsilon dash, rather it is the Euclidean distance. It will be the Euclidean distance between point P and point Q, right? Now this is again a visual representation, and the same examples which the same formulas which I discussed here, definitions and the visual representation which I discussed here are replicated here, where we know that the value of, because we will have the upper bound of epsilon which we will be giving to the algorithm. For example, we give this algorithm the upper bound of 4, so we will be computing epsilon dash for each point by setting it to 1, and we will see if the point becomes the core point. It does not become the core point, then we will give it a value of 2. We will see if the point becomes the core point, no, then we will give it the value of 4. And when for example at value of 3 it becomes the core point, then this 3 is set, this very value is set for E dash, right? So now this is sort of an example where this optics algorithm is executed for multiple points in the data. If you see here, this is, okay, let me number it. This is step 1, where one point is picked, and for this point various computations are performed to find the epsilon dash for that variable, for that point. And then when the this point becomes the core point. So within its radius, what is done, that distance between other points and this point is computed, if you see here, right? And this distance computation will be in a specific order. For example, maybe for first this point is processed, then this point is processed, and then this point is processed, right? So once we have computed these values for this point, then we will be considering the next point, right? And then the same process, computation of distance measure for the next point will follow. And once this is done too, and we can call it 1a, we can call it 1b, and we can call it 1c. This will become 1a, this will become 1b, and this will become c. And then the third step is the next point we take, and then we compute the e dash. And once the e dash is computed, which makes this point as a core point, after that from the rest of the points we will be computing the reachability distance, right? So this will become 3a, 3b, and 3c, and this process continues for the n number of points in the data, right? So primarily what we are doing here is we are storing these two values for each and every data point which is there in our data set, right? Now once this is done, then we need to plot a graph. This is sort of visually it represents like a histogram, but actually it's not a histogram. So we need to plot a graph which is called, this particular graph is called the reachability plot. So reachability plot is a bar chart that shows each object's reachability distance in order the objects were processed, right? So what we will do, if we see here, rather that was a better example. Here we process this point first, so we are labeling it 1. We process this point second, then we are labeling it 2, and then this point was processed, so it is labeled 3, so on and so forth, right? So in the order in which the data points were processed, so what we are doing here is we on the x-axis we will have 1, 2, 3, 4, 5, 6, 7, so on and so forth, and here we will be plotting the reachability distance of object 1, and here we will be plotting the reachability distance of object 2, and then 3, and maybe object 4, so on and so forth, right? So once we have done this, right, so for this the whole of this computation will be required, and then we plot the reachability distance or reachability plot of the complete data set. Then we will have some this type of a graph, and here what does this graph show? Here we will set a threshold. This we can do visually in a better way. For example, we make a cut line here, for example, at this point, right, this red line. Now the number of ditches, if you see there, here number of ditches or number of valleys which are below this this cut point, right? So here this is 1, it's 2, and it's 3. So the number of ditches shows the number of clusters in your data set. For example, let me change this threshold, let me use the blue color, and instead of making a threshold here, let me make a threshold here, right? Now if you see here, using this blue threshold, every data is almost in the same cluster. So here this blue line shows, identifies a single cluster, but this red line tells us that there are 3 clusters. Okay, let us use another cut point. If you, for example, I make a green line here, and okay, इसको मैं touch करना चाह रहा हूँ. If you see here, now this green threshold tells us that there are 4 clusters. This is 1, this is this small one is 2, then obviously this is 3, and this is 4, right? So this is how optics works. But if you notice, this optics is not giving you exact clustering, right? It is not telling you that which data point lies in which cluster, right? It is just telling you the number of clusters which can be in your data, right? This if and keeping this point in your in view, if you now read the title of the algorithm, so it states that ordering of points to identify clustering structures, right? And then once you have understood optics, you will be able to understand as well that the number of clusters which are identified strongly depends upon the sequence in which these objects are picked as well, right? Because for example, this could have been a graph like this as well. For example, points were like this, then in that particular graph it would have been very challenging to identify the number of clusters. So this actually is highly dependent on the order in which the objects are picked to perform clustering. So here if you see, this is an example of a very large data set where you can find 3 or 4 clusters in the data, although it depends upon where you put your threshold, right? So this is how the optics helps you find the the orientation of the data for your unsupervised learning, right? So that's all regarding optics. Next we will be doing hierarchical clustering.